Today, we're learning about doubly linked lists, an enhanced version of the singly linked list that allows traversal in both directions. Remember singly linked lists? Each node pointed only to the next node. You could only move forward. But what if you want to go backward? A doubly linked list solves this problem. Each node now has 2 pointers instead of 1. One pointer points forward, one pointer points backward. You can move in both directions. Look at the animation. See how arrows go both ways between nodes? That's the power of doubly linked lists. Node structure 3 parts. Every node in a doubly linked list has 3 parts. First, the prev pointer. This stores the memory address of the previous node. For the first node, prev is null because nothing comes before it. Second, the data. This is the actual value we're storing. Third, the next pointer. This stores the memory address of the next node. For the last node, next is null because nothing comes after it. Watch the visualization. Each node shows prev in red, data in blue, and next in green. The colors help you see how nodes connect in both directions. Head and tail pointers. A doubly linked list maintains 2 special pointers. Head points to the first node, tail points to the last node. Why keep both? Because with tail, we can insert at the end in O of 1 time. In singly linked lists, inserting at the end required traversing the entire list. That was O of n. Now it's constant time. This is a major advantage of doubly linked lists. Insert at head, O of 1. Watch the insert at head operation. Step 1, create a new node. Step 2, set the new node's next to the current head. Step 3, set the current head's prev to the new node. Step 4, update head to point to the new node. 4 operations, constant time, O of 1. Insert at tail. Now watch insert at tail. This is where doubly linked lists shine compared to singly linked lists. Step 1, create a new node. Step 2, set the new node's prev to the current tail. Step 3, set the current tail's next to the new node. And Step 4, update tail to point to the new node. Again, 4 operations, constant time, O of 1. In singly linked lists, this was O of n because we had to traverse to find the tail. Bidirectional traversal. The biggest advantage is bidirectional traversal. You can start at head and follow next pointers to reach tail, or you can start at tail and follow prev pointers to reach head. Watch the forward traversal animation. We follow next pointers. Now watch backward traversal. We follow prev pointers going the opposite direction. This is useful when you need to search from both ends or check if a list is a palindrome. Deletion is easier than singly linked list. In singly linked lists, deleting a node was tricky. We needed to find the previous node first. That required extra traversal. In doubly linked lists, every node already knows its previous node through the prev pointer. To delete a node, we simply update its neighbors. We set node.prev.next equal to node.next. We set node.next.prev equal to node.prev. The node is now disconnected. Deleting at head or tail is O of 1. Deleting in the middle is O of n for the search, but the actual deletion is O of 1. Time complexity comparison. Let me compare with singly linked lists. Insert at head, both are O of 1. Insert at tail, doubly is O of 1, singly is O of n. Big improvement. Delete at head, both are O of 1. Delete at tail, doubly is O of 1, singly is O of n. Another big improvement. Search, both are O of n. We still need to traverse. The trade-off is memory. Each node uses extra space for the prev pointer. Common mistakes. Let me warn you about common errors. First, forgetting to update both pointers. When you insert or delete, you must update both prev and next. Missing one breaks the list. Second, wrong update order. Always set the new node's pointers before changing existing links, otherwise you lose references. Third, edge cases. Handle empty list and single node cases carefully. Check for null before accessing prev or next. Fourth, forgetting head and tail updates. When you insert at ends or delete from ends, remember to update these pointers. Real-world applications. Doubly linked lists are everywhere. Browser history uses them. Click back, you follow prev. Click forward, you follow next. Music players use them. Previous song follows prev, next song follows next. Undo and redo features in text editors. Undo follows prev to earlier states, redo follows next to later states. LRU cache, the least recently used cache, uses doubly linked lists for efficient removal. Closing. That's doubly linked lists explained. Remember the key points. Each node has prev, data, and next. You can traverse both directions. Insert and delete at both ends are O of 1. Practice the operations. Watch how both arrows update when you insert or delete. For more attractive animated tutorials on data structures and algorithms,